The talk I'm giving is planning your home solar system with a battery. I'm still an adjunct associate professor at both James Cook University and the University of Adelaide. I'll start with the introduction. The installed price of solar PV, rooftop PV, has been falling about 15% per year. At the present cost of power, it makes it more economical for people to generate their own power. And in this talk, solar means rooftop solar rather than big grid solar. Home batteries allow people to store excess solar power for use later and thus hopefully reduce their bills. One of the things that's actually making the Hornsdale Power Reserve, that's a big battery in South Australia, very profitable, is something that's called Frequency Control Auxiliary Services, FCAS, which is basically the sort of controls in order to keep the network frequencies stable. And batteries are really good for that. And your home battery can be part of a virtual power plant, which then can provide that FCAS, and that makes it very profitable for the network retailers. So this is the falling cost of rooftop PV. And at present in South Australia, our import tariff is 36 cents per kilowatt hour. In North Queensland, it's 26 cents per kilowatt hour. So we have a privatized system, and in North Queensland, it's government controlled. So much for privatizing, giving cheaper prices to the customers. In South Australia, our export tariff is 14.2 cents per kilowatt hour. In North Queensland, it's 7.8. If you put on solar PV, that's roughly 2.7 cents per kilowatt hour if you write it off over a 20-year period. So that's actually much lower cost than any of the tariffs that we've got. So I've got a solar system, and the payback on my house is 3 years, but typically it's 3 to 4 years. And on my system, I get a rate of return of about 30% per annum on my investment. So that's much better than buying shares. If you're in Queensland, it's 16%, and it's basically pretty well guaranteed, so still much better than buying shares. So at present, more than a third houses in South Australia and in Queensland have rooftop solar. It simply makes economic sense. And this is the forecast growth of solar PV. And if we, in South Australia, which is the green curve, the second curve there, the total demand is about 3 gigawatt. And with the forecast growth of solar, the full demand can be met by rooftop solar. In pretty well the same applies in Queensland. The maximum demand is 10 gigawatt, and you can get about 8 gigawatt from rooftop solar. So that's actually going to make some real problems, and that's called the duck curve. This is the plot of the demand in 2016, and that's 2022, 2030, and in 2030 they expect the average demand in the midday to be negative. And one way to see how fast that actually goes, in South Australia, the minimum demand before 2019 was 583 megawatt. In 2019, that dropped to 446 megawatt, and in 2020, it dropped to 388 megawatt. So nearly 100 megawatt per year drop, and you don't need too many years before you end up with negative. At the moment, about half the substation areas in where I live have got negative flows of power, so people exporting power. When you have everybody has a negative demand, then that can lead to over voltage, and that can lead to solar inverter trips. And if everybody's solar inverter trips at exactly the same time, that can lead to load and generator instability and blackouts. And AEMO is getting really worried about this, and they want to get variable feed-in tariffs and control PV inverters so that they can actually remotely control off people's PV inverter. And if they can't do that, then they'll actually have to limit new people joining and putting solar on their roof. Batteries, as I will show, will really solve some of the problems there. And the government in South Australia encourages batteries, and we actually have a subsidy for installing a battery. So let's have a look at different batteries. Lead acid battery, you can only discharge them to capacity of about 40% and about 3,000 cycles, and it's quite expensive. So you wouldn't want to use that. Lithium titanate is a new type of battery that's being developed and is available. It's about twice the price of other batteries, but also lasts twice the number of cycles. So it's actually quite a good investment. Typical warranty periods for those are about 20 years. Lithium iron phosphate are the batteries that BYD have, the Chinese manufacturers, and they've got quite good performance. Lithium manganese cobalt is what, and the lithium nickel cobalt oxide are batteries which are used by different manufacturers like Tesla, and they do have some problems, but they have a much higher energy density, which makes them very suitable for cars. Zinc bromide flow batteries are made by Redflow, and they're actually quite a good battery with a good long life as well. And vanadium flow batteries are some that have got even longer life, but the market for that has gone strangely quiet in the last half a year. The Australian lithium-ion battery test centres installed 8 batteries in May 2016. Only 4 of those were still working in April 2019. So the reliability of the battery systems at that time weren't all that fantastic. Of the 10 batteries installed in June 2017, only 3 were still working without faults in 2019. And that's not a very good reliability. Most manufacturers give a 10-year warranty on the battery, but you want to make sure that the manufacturer is still in business. And several manufacturers have disappeared. Technology is improving, the batteries are becoming more reliable, but of course it's pretty hard to predict reliability of your battery 20 years ahead. Let's have a look at safety. Lead acid batteries produce gases when charging, and that's got a risk of explosion. Lithium, nickel, cobalt, aluminium has got highest energy density, but it's got thermal runaway when the battery is more than 150 degrees Celsius. The lithium, nickel, manganese, cobalt is used in Tesla, LG Chem, and most mobile phones. We've got a thermal runaway when it's greater than 240 degrees C. And the battery management systems are designed to prevent that. Those fires have resulted in a new Australian installation standard for batteries that require fireproof shielding. So and that applies to all batteries. Now, lithium ion batteries have got no thermal runaway problems and are much safer, but they still have got to be have fire-proof shielding behind them. The flow batteries are safer still, but the new Australian standard says anything that's not a lithium-ion battery has to be housed outside in a fireproof enclosure. So the flow batteries that can't catch fire have to be installed in a fireproof enclosure. The standards are a bit crazy. Now let's have a look at the prices of the battery packs, and this is the price since 2010 to 2019, and the battery pack price has been dropping about 20% per year. So if at the moment it's about it's 156 US dollars. If you extrapolate that, that will be $13 in 2030. So you can see when at the moment much of the price of an electric vehicle is in the battery. By 2030 it will only be a very small percentage of that, and battery electric vehicles will be cheaper than petrol cars. If we look at the home battery system, at the moment the price is about $900 per kilowatt hour. By 2030 that will be about $300 per kilowatt hour, so that's a significant drop in price. And that price actually assumes that the installation is the same cost, the hybrid cost of the inverter halves, and the battery pack drops at the 20% per year. Now, virtual power plant, by giving the electricity retailer control of your battery, and they can discharge your battery when the price is very high and charge it when the price is negative. As an example, if we take a 12 kilowatt battery and the retailer discharges at 80%, and they discharge your battery when it's the wholesale price is $14,700 per megawatt hour, which is the maximum, then the retailer earns $141 by discharging your battery and pays you $2.80 at the feed-in tariff rate. If quite often the price goes negative, and if the price is minus $1,000 per megawatt hour, which is the maximum, the retailer earns $9.60, and you've got to pay $3.36 for the privilege of him charging your battery. Frequency control auxiliary services, FCAS, are much more profitable than that for retailers, and most virtual power plant schemes limit the discharge to 20%, so that you will always have some battery for that battery backup. In South Australia, the government sponsored a virtual power plant, and this is an event that happened when the 748 megawatt turbine at Cogan Creek in Queensland tripped, and the South Australian virtual power plant worked automatically as expected, and everybody's home battery here put power back in the grid in response to a turbine in Queensland tripping, coal-fired station. On this graph, there's a limit of 150 millihertz on either side of the 50 hertz, and when the frequency at the trip, which was just up there, went outside the limits, then the battery, the virtual power plant responded, and this was the what they expected the power plant to do, and it actually did more. So it worked much better than expected. Here's another graph of the virtual power plant, and you've got an excursion when the frequency is too high and the power plant charged, and here's an excursion when the frequency is too low and the virtual power plant discharged, in order to actually correct for that. Now this is actually quite good for the retailers. For instance, the virtual power plant revenue for 3 months from 12th of January was $225,000. From the 13th of January to the 12th of February, just 1 month, they earned $1 million from the virtual power plant. And if we say, take about 400 batteries for that, that's $3,100 per battery for the 4 months period. So that's actually quite good, seeing that typically they pay you $200 per year for having your battery as part of a virtual power plant. Let's have a look at the battery, how you can configure a house with solar and a battery. And of course, the same applies to solar. So we've got our solar panels, and if you have a battery and you do it from scratch, you're best off to have a hybrid inverter, and you can either have a single phase or 3-phase. And your battery connects in that as basically with the DC. Now, many batteries are 50 volt. Your solar panel might have about 500 volts, something like that on it. So you've got the separate DC-DC converters and DC to AC converter. You have current sensors in your line, current transformers, in order to actually then control that, so that you charge your battery when you've got excess power going out. So for some of the time, your solar panel will actually provide power, and it comes straight back into your house, and the net outflow is nothing. You can have commercial inverters available, typically up to 10 kilowatt maximum, and a battery is typically 5 kilowatt maximum. And you need 3-phase meter and 3 current transformers to control the battery, even if it's a single-phase battery. You can have a single-phase inverter, so that you put power out on single phase, and then you've got your solar panel with your battery and single phase hybrid inverter. Depending on your system, you can actually have that black phase as a battery backup, so that if the power fails, then the power gets turned off here, but your hybrid inverter can still actually produce power. So that's a DC coupled battery. You can also have an AC coupled battery. So the Tesla Powerwall, for instance, is a battery with a battery inverter, and that is a single phase inverter and connects to 1 phase. And then you again have your 3 current transformers, etc. So that if the power fails, circuit breaker operates just up here, and this phase stays on, and your solar inverter would actually also stop working under those conditions, because there's only single phase power available. And we'll talk about that more in a little bit. There are some rules on this, and as time goes on, these rules were becoming more tight in order to prevent the duck curve getting too bad. So at the moment, if you've got single phase, a house with single phase or 2 phases, then the PV inverter size should be less than 10 kilowatt. And on a 10 kilowatt inverter, you can actually have 30% more solar panels, so you can have 13 kilowatt solar panels on a 10 kilowatt inverter, but you must export limit this to less than 5 kilowatt. So you're not allowed to export more than 5 kilowatt. If you've got a PV and a hybrid battery, exactly the same applies. 10 kilowatt, but export limit to 5 kilowatt. In North Queensland, if you export more than 2 kVA, then you must export lagging power, or your inverter must be capable of a volt-var mode, which means if the voltage gets too high, it becomes you export lagging power, and if it becomes too low, you export leading power. Single phase rules apply for each phase if you've got 2 phases. If you've got 3 phases, it's a little bit different. You can have, you're still limited to 10 kilowatt per phase, so 30 kilowatt total. In South Australia, the unbalanced shall be less than 5 kilowatt. In ERGOT, you can, as long as you export less than 15 kilowatt, you're okay. In South Australia, if you add a battery, then each phase must be limited to 5 kilowatt. And the ERGON and South Australian Power Networks websites give details of those rules. That's a picture of my house. This is a 2 kilowatt solar panel system, which initially was on that roof. And then I did the calculation, and in 2018, we upgraded the system, shifted that one to the east facing roof, and that's the north facing roof. In addition to that, this solar panel's got a 3-phase inverter, which you can see there. And we've also got a behind the meter, which records 5-minute data. And I used that data in order to work out whether it was economical to buy, or to determine when it was economical to buy a battery. We've installed a battery on the 28th of April, so that's just a month ago. It's an AC coupled battery, Tesla Powerwall, and the maximum charge and discharge that can do is 5 kilowatt and 13.5 kilowatt hour total capacity. Our house is carbon negative, so that we actually generate 1.76 times our total consumption for our house. We've got an all-electric house, and the total consumption, including our hot water, we generate more than that. So we've got a carbon negative house. But because we get much less money for our export, we still got to pay a little bit of the bill until we got the battery. So if we look at the configuration, we've got a single phase inverter for a 2 kilowatt system that we don't really know how much it's producing, apart from some clever analysis that I can do. This is the 12.2 kilowatt system, is 3-phase inverter. Then we have our smart meter and our mains isolating switch, behind the meter meeting, 3 current sensors. And on the 1 phase, the black one, we've got an isolating switch, which is our backup system. And our power and light is connected on the backup system, which is with the battery and the battery inverter. So if the mains fails, we can't use our cooking or air conditioner, but we can use our power and light, so we can basically keep doing what we like doing. So let's have a look at the economics. The average price at the moment for a 7 kilowatt system installed is $6,010 in South Australia and $6,870 in North Queens and in Brisbane. I'm not sure if it's more expensive in Townsville, but I expect it to be similar than in Brisbane. So you're looking at roughly 90 cents per kilowatt hour. typical ads for a 6.6 kilowatt system, that's the maximum you can put on a single phase, is about $3,700, so that's about 56 cents per kilowatt. And that is, all of these prices are when you assign the small technology certificates to the installer. And a small technology certificate is a government contribution where they basically pay for the equivalent carbon tax that are generated by the solar system during its lifetime. So if you look at panels by themselves, they're about 70 cents per watt. Microinverters are about 70 cents per watt, and STC about 60 cents per watt. So pretty well your STCs pay for the cost of the solar panels. A reasonable installed price is about 0.7 cents per watt for string inverters and about $1.4 per watt for microinverters. Now, microinverters are little inverters that sit behind the solar panel, and if part of your string of panels is in shade, then if you've got a string inverter, if one panel is in shade, then you'll lose the power from the whole string. But with microinverters, every panel produces power and all the power simply just gets added up. So if you've got trees around the house, you've got to use microinverters. Typical payback in South Australia is about 3 to 4 years for string inverters and 5 to 7 if you use microinverters. And in North Queensland, it's about 35% longer. The panel warranty is normally greater than 15 years, so it's really a no-brainer. It pays off long before the warranty of the panel is expired, and typical inverters have got warranties of 10 years. So my 12.2 kilowatt solar panel with the 3 inverter is on track for payback of 3 years exactly. So when I upgraded our system, I installed the behind the meter to get input, output, export, PV power, solar power used, mains voltage, etc. at 5-minute intervals. And I've been looking at that data since that system was installed. And the data for the whole year of 2019 is presented in some of the graph later on. The PV alone will give me a self-sufficiency of 45%. With the PV plus battery, I get 83%. That's if we exclude the hot water. And we've got an all-electric house, we've got no gas. This is a plot of my power demand during 2019. So this bottom one here is the cooking. The brown one is the power and light. And you can see that's fairly constant during the year. The red one is our air conditioner. And you can see, hey, when we get hot days, and in South Australia, we actually got some 40 degrees, 45 degree days here. And then that uses a lot of power. And also we've got fairly consistent power in the winter. And yeah, my air conditioner is working nicely as a heater at the moment. And it's 20 degrees in my room. This green curve is the the blue curve is the total consumption demand. The green curve is the import. So this difference is actually the amount that the rooftop solar saves averaged out. And of course it does more during the day than at night. And you can see it's actually quite consistent and a good saving. What I've plotted on this graph is the PV generated. So this curve here is the PV that is generated. This curve is the solid lines, is the actual radiated power in Adelaide. That's the nearest I can find. That dotted curve is the radiated power in Townsville. So in Adelaide, in the winter you get half the average solar radiated power. In the summer you get 1.5 times. That difference is far less in Townsville. So if you want to have you can have a solar panels lying flat on the roof, or just a slight shift to the north in order to increase the power there and reduce the power there. Now, if we look at this, this curve here, that curve there is my export. So you can see in the summer, I export a lot more than I import. The blue curve is my consumption, and the brown curve is my import. In pretty well most of the year, I export more power than I use. It's interesting. So this is the import during 2019. This is the dotted line is 2020, and it follows the 2019 line. And this is where we installed our battery. So that difference is our battery, and my import power dropped. And of course, my export power actually dropped at the same amount, but I would get the plot too confused if I put it on there. So you can see the system actually works quite well, including the battery, and the battery will fill for most of the time. It's interesting here where I live, the heating is the largest power use in the winter. In North Queensland, of course, you don't need to heat in the winter, but you do need to cool in the summer. This is a plot of the battery calculations from the 5-minute data on whether the battery fills up. So it'll fill up all of the summer and all of the spring. In some of the winter time, it may not completely fill, and it will discharge completely. In the summer, we use less power, so your battery won't actually fully discharge most of the days. So the blue curve is the actual battery usage. So even in this situation, I've considered a 12 kilowatt battery and a 14.2 kilowatt PV, and much of the time you don't actually use the full capacity of the battery. Of course, if you talk to the salespeople, they say, oh, you fill it every day and you discharge it every day. That's not the case. So that's a picture of our battery, which got installed just over a month ago. And if we have a look at this curve here is the solar power during May, and that's the only whole month of results I have. The green curve is the battery, so the battery charges up during the day on average and discharges during the night, during the evening. The black curve is the power that we supply to the grid and draw from the grid over the day. The red curve is the power that we supply to the grid and draw from the grid when we have the battery. One thing which is noticeable is that, first of all, this slope is much less with the battery. And secondly, the evening peak is basically purely supplied by the battery. So that it really makes it much better for the electricity supply people to provide keep the network stable. Notice in May it's got the 67% of the average solar radiation, so it's one of the lesser solar powered months. And on average, we've had 11.5 kilowatt discharge from the battery. 4 days, it wasn't able to fill the battery, and the battery saved me $70 in the month, or $2 per day, which isn't all that fantastic. So let's have a look at the summary of that. And these are the import tariffs, export tariffs, hot water tariffs. And so you can see in South Australia, we've got a much higher import tariff than North Queensland, but we also have a higher export tariff. For the battery, for 12 kilowatt, my calculations are that you use about 82% of the capacity average. So if you've got no batteries, here our cost would be that. In North Queensland, the cost would be that. If you install the PV with the same amount that we have and the same usage that we have, your bill would for the year would be $241 or $922 in Queensland. So in South Australia, we'd save $4,102. In North Queensland, you'd save $2,500. So not quite as much, but still, hey, $2,500 for a system that you can install for pretty close to $10,000. It really got a good saving. If we add the battery, then I'm expecting my total bill for the year to be minus $500. In Queensland, you'd still have to pay $300. So your battery saves about $737 in South Australia and $620 here. So if we look at the return on investment, then in South Australia, the solar PV, we're looking at near enough 40% return on investment, which is pretty good. In Queensland, 16.3%. For the battery, in January, the price of the battery dropped. So between mid-January and mid-April, when the government subsidy reduced, the cost of the battery, and we bought it then, was $4,500. The government subsidy reduced by $2,000, so the price of the battery is now $6,500. And so the return on investment for the battery went from 6% to 1.7%. If you do the calculation in Queensland and there's no subsidy at all, you're actually losing 3.4%. We can get a pretty good equation for the saving of the battery. You've got 365 days per year. The 12 is the average capacity of the battery. And for Tesla Powerwall, 13.5 kilowatt hours. That drops to 70% by over 10 years. The average battery capacity is about 12 kilowatts, so we use that. And then we take the magic multiplying factor is 0.82, which is the average capacity that you use. And then you put in the import tariff and the feed-in tariff. Now the feed-in tariff, you've got to divide by 0.9 because there is a loss. You have to put more battery more power into the battery than you get out, and it's there's a 10% loss, return loss, going through the battery. So when you do those equations, we get pretty well the numbers that we calculated. Of course, if you talk to a salesperson, he'll say, well, you got 365 days per year. That's the capacity of the battery. and that's the sort of difference between the import and feed-in tariff, and you save $1,000 or $800, so it's very optimistic. Also, if you work out the battery, the total system, it's very optimistic. If you look at the solar plus the battery, so you want to make sure you keep them separate. So what I've done is I've looked at the difference between import and export tariffs. This is what we have at the moment. That's the price at which I bought my battery, the blue curve, and I've included the virtual power plant, and the virtual power plant gives me $1,000 reduction in the price of the battery. So I've got the 6.4 years payback period. At the moment, if I were to buy a battery, I get less government subsidy, and I'll be on the green curve, and we're looking at 9.5 years. And 9.5 years payback for a 10-year warranty battery isn't really worthwhile. If you look at the price for North Queensland, this is the curve for North Queensland, because there's no subsidy. And this curve here is flat because that is when we have zero feed-in tariff. So it's really not worthwhile to have a battery in North Queensland at present. This curve here is if we have a $7,000 drop in cost of the battery. So either with a government subsidy, just the same as the South Australian government had, or wait till 2030 and you'll be at this price then. And you can see under those conditions, the battery has got quite a good payback period. And again, it's got a flat bit with no feed-in, with zero feed-in tariff. So even if they don't do feed-in tariff, you can still, your battery will still pay back. Now, you may not have access to full data like I've had. So you can go to a typical solar and battery payback calculator. And the one I've done here is use Solar Choice. And I put the tariffs in, and I put a roof, 25-degree sloping roof in South Australia, and a flat roof in Queensland. And then you can calculate what payback periods and return on your investment you can get. You can see the payback periods are fairly similar to what we calculated, and also in Queensland. The return on investment, the payback, the calculator says is 42%, and my calculation on actual data says 39.7%. That's pretty good. In North Queensland, the difference is a little bit worse. They reckon 26% when I calculate 16.3%. And it may be somewhere in between, but that's still a pretty good payback. For your battery, in February it was 7.3 years, and my calculation said 6.4. Now it says 10.9, 10.5. My calculation says 9.5. North Queensland's greater than 20 years. My calculation said 20 years. The investment, they calculated 10% on the battery, and I calculated 6. And you can see the results are fairly similar. Most salespeople will not quote the return on investment for battery because that doesn't look very good. Nobody will pay money for that. But when you lump them two together, you can say, oh, you can make 11% profit on putting solar and a battery on. Yes, but you can make 26% profit on these calculations if you only put solar on. So beware of salespeople. You really need detailed calculations and separate quotes for solar and separate quote for battery. There are some other considerations. Well, first of all, by putting solar on, you use less fossil fuels. With my system going in, I produce 3.6 megawatt hour per year, and that's a significant reduction in carbon dioxide. I can be a part of keeping the supply stable by being part of a virtual power plant, and I've signed up for the virtual power plant. We can be more self-sufficient, and with the battery, my self-sufficiency is 82%. You can have a battery backup. I've got underground power, and the power failures are very, very infrequent. If you have overhead power, it's more frequent to have power. If for my system in South Australia, if I buy the battery now, it's $6,500. The average power outage in Australia is about 2 hours. My usage during that time is 2.14 kilowatt. So my battery backup, if we purely get the battery for the battery backup, we'd be looking at $303 per kilowatt hour, when in North Queensland you can buy it for 26 cents per kilowatt hour. So you don't want to put a battery in for battery backup, but it will guard you for cyclones, bushfires, etc. So, or you can say, hey, put my money for where your mouth is, for any of those 5 above, and that's basically what happened with me. It was to really toss up, shall I go for battery? And I thought, well, being part of keeping the network stable with a virtual power plant and reducing the greenhouse gases is good. When you have a battery, using a heat pump for hot water becomes more economical. In the future, we'll have changes in tariffs, and the battery payback is very much related to the tariffs. The export tariff is likely to reduce with the duck curve, and the import tariff in South Australia is likely to reduce next July. We'll probably get time variable import and export tariffs in order to actually manage this duck curve. And we may have a high input tariff during the morning and evening peak, and a battery is really good for that. So batteries may become very economical when we get these changes to the input tariffs. Tariffs will also change with distributed energy management or demand side management. Batteries, air conditioners, hot water pool pumps, etc., can all be controlled by either the consumer or the retailers, with little inconvenience to users. In South Australia, the peak demand is often at midnight, because when the coal-fired power stations were basically the only power that stations providing power, they had very low demand at midnight, so that's when they set time clocks in the meters to turn the hot water systems on. And that still happens. At the moment, of course, you want the hot water systems to switch on during the daytime when everybody produces solar power. In Queensland, they've had ripple control, and they've had the capability for doing that. In South Australia, it's only with the smart meters that they can do that, and they still don't use it. I've got a smart meter, and my hot water system turns on at the middle of the night, and quite often the biggest power demand is in the middle of the night when the hot water systems turn on, and quite often the highest power prices or also during the middle of during that time. So those tariff changes can easily be implemented with smart meters, and that will make batteries more economical. The third guess for the future is the battery cost. Government incentives will reduce over time. Battery costs, if they drop at 20% per year and inverters half per decade and the installation is the same, the battery without subsidy is now the Tesla Powerwall battery is now 11,500. In 2030, that will be 3,800, and 2040, 2,300. And at 3,800, it'll become very economical because that's less than what I paid now for my system. Government regulations will change, and when the government introduced the new fireproof cladding requirements for battery systems, they estimated that would increase the average installation cost by $1,000. And in my house, I actually put the battery on a different wall because of that, on a wall where it wouldn't require fire cladding to keep the cost down. But that meant the actual cable length was a little bit longer, and so the costs still went up for mine. The virtual power plant incentives are very profitable for retailers and for householders. Tesla is preparing a launch for a 1,000,000-mile battery for their cars, and increasing battery lives improves the economics. You can use old car batteries in home batteries, and that will make the home batteries cheaper. We can have different battery types. At the moment, a home battery is typical 10 kilowatt hour and 5 kilowatt power capability. An Nissan Electric Leaf has got a 40 kilowatt hour battery. It's got bi-directional capability, and you can plug it into your power point at home and get vehicle to the home, or you can get vehicle to the grid. AEMC is working on regulations from that, and manufacturers also doing that. And that will be a really big change. And Volkswagen predicts that it will have access for the vehicle to the home and vehicle to the grid of 360 gigawatt hour of batteries in 2025, and 1 terawatt hour by 2030. Volkswagen wants to become an energy retailer as part of that. It can actually be used to off-grid your house. And if you have your car as a battery charger for your house, if you don't have enough charge anymore, you drive to instead of the petrol station, local charging station, charge up your battery, drive home, and you can run your house again. So the electric car for home battery may make home batteries uncompetitive. Battery technology will change. Solid-state batteries will be available, and that will make batteries last much longer. So there'll be big changes happening in all of that. So in summary, at present, home batteries are not economic. Other factors may tip the decision at present. My first and second PV systems, and they were 7 years apart, and the price per kilowatt hour reduced by 4.2 times in that 7 years. The batteries and PV are on a similar reduction in price, and just like the PV increased in performance, and typical panel on the first system was 250, and the second system 300 watt for the same panel size. You will have the same sort of changes in batteries. And in 20 years' time, most residents will have PV plus battery. It was a payback period of less than 3 years, and it'll be economic to supply all the power for your house and a car. And most Most EV batteries, electric vehicle batteries, will be charged from your rooftop solar, and the feed-in tariff will be very small.